This presentation is going to discuss how information is stored inside the computer. Information is stored in random access memory, or sometimes just called memory, and there are two different types of information we store, the instructions and the data. The instructions are programs that tell the computer what to do. The data is the information that the programs operate on. They manipulate the data, they calculate new values, they work with the data, but the programs that you write are the instructions. Memory is organized into different size storage units, beginning with the very smallest unit, the bit. And the bit is simply a 0 or a 1. It stands for a binary digit. Many people wonder why we didn't use base 10. Well, they tried that. They had 10 different values. The voltages drifted, the numbers got mixed up. So we went to the most basic representation they could, and they said it's either got lots of voltage or it has no voltage, and we can tell the difference, and that's why they went to base 2. It is simple and easy. Now, a bit stores very little information, so we have to combine them all together into a larger unit of storage called the byte. And the byte combines 8 bits to give 256 possible values, which go from 0 up to 255. Down here we see that 8 bits are combined to make an entire byte, and half a byte is referred to as a nibble. This is the smallest unit of memory which can be addressed. But it's still pretty small. You've only got 255 or 256 possible values. So they combine that into a larger storage of unit called the word. And the word is kind of a natural storage unit for the machine. And what that means is when the CPU loads things from memory or stores things back into memory, it typically does it a word at a time. The size of a word varies depending on what your CPU is. Is it a 16-bit CPU, a 32-bit CPU, or a 64-bit CPU? And all of these have different sizes of memory that they can address. So we're going to be talking about that in a couple more minutes. Now we want to look at hexadecimal numbers. And hexadecimal are base 16 numbers. And you're probably wondering, well, why in the world would they use base 16? Well, base 16 numbers have 16 digits, which go from 0 up to 9, and then they switch to letters A, B, C, D, E, F, so that they get a total of 16. The reason we like it is because we can write really large numbers with a fewer number of digits, because every digit represents more possible values. So every digit represents 4 bits of information. Now let's have a little look at how number systems work, and this might start to make a little bit of sense. So let's have a look at how a number system works. We're going to start with base 10 because we're always familiar with it, and we're going to look at a number like 132. 132 is 1 times 100 plus 3 times 10 plus 2 times 1. And you probably learned that sometime in school, maybe you forgot it, but it's pretty obvious that 100 plus 3 plus 2 adds up, or 100 plus 30 plus 2 is 132. Now, these asterisks represent multiplication, and we use that symbol all the time. One of the other things I want you to notice is that this 1 is 10 to the power of 0, because anything to the power of 0 is 1. The 10 is 10 to the power of 1, and the 100 is 10 to the power of 2. So it goes 10 to the power of 0, the power of 1, and the power of 2. And that's how you get the various digits. And that works that way in every number system. So let's go down and represent 132 in base 2. Here, the powers are not 10 to the power of 0, but 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, the power of 4, 2 to the 5th, 2 to the 6th, and 2 to the 7th. So we can say, well, what is 132? Well, it's 1/128th, which is the biggest power of 2 less than 132. So that's 128, but there's 4 left over. So 4 is left over. There are no 64s in 4, no 32s, no 16s, no 8s, but there's one 4, and that means, well, we've now used all the numbers. We've got 128 plus 4, that gives us 132, so we don't need any more. So we put zeros for the rest. So we can read this out as a binary number as 1, 0, 0, 0, 0, 1, 0, 0. And it takes all those digits to represent 132 in base 2. So we see that the smaller the base, the more digits are necessary to represent the same number. Now, finally, I want to look at base 16, show you how it works. Here, things are in powers of 16. So 16 to the 0 is 1, and 16 to the 1 is 16. Well, 8 16s are 128. So that's cool. That means there's only 4 left over. So with 4 times 1 is the 4. So it becomes 8 4 in base 16. Now memory is addressable from 0 up to however number bytes you bought. So whenever you buy 4 gigabytes of RAM, you can address it byte by byte from 0 up to whatever the biggest number is. You cannot address below the byte level. This is the way memory is laid out. It starts out at address 0. Now you notice that's 0x00. 0x is a notation that means it's written in hexadecimal. So this is base 16 numbers appearing already. So it goes 0, 1, 2, and then 3, 4, up until FFFFF, which is the largest possible base 16 number. And that gives you the entire range of memory, and you can address it byte by byte. Now, memory comes in various sizes. You could always talk about the number of bytes, but bytes aren't very big, so we tend to combine them into kilobytes, which is 1024 bytes. Now, everybody thinks kilo is 1,000, but in the computer business, 1,000 is 1024, which is 2 to the power of 10, and things are based on powers of 2. A megabyte is 1,000,000 bytes, or 10 to the 16th. A gigabyte is 1,000,000,000 bytes, or 10 to the 9th. A terabyte is 10 to the 12th. A petabyte is 10 to the 15th, and an exabyte is 10 to the 18th. The size of memory is limited by the word size because when you store an address in a word, you can only store a number so big in one word, and that's our limiting factor. So if you've got a 32-bit machine, you can only store 32-bit addresses, which gives you the ability to address 4 gig of RAM. You can't have more than 4 gig of RAM in a 32-bit machine because you can't generate an address bigger than that. So we go to 64-bit machines, and they can address 16 exabytes. Now you probably think 16 exabytes, wow, that's a lot of storage. And it is today. But a few years ago, we thought we'd never hit a 4 gigabyte limit, and we've passed it. So 10 years from now, we might be thinking in 16 exabytes is not that big. Who knows? Finally, I mentioned at the beginning of this that instructions and data are stored in different parts of memory, and they're stored separately. So you can get a segmentation fault, which happens when you try and perform calculations as instructions or on instructions. So you take an instruction and you treat it like data. You try and add 2 instructions together. Well, it doesn't work. Or you say, here's an address, go there and execute that instruction, and it's not a valid instruction, it's a piece of data. Both of these cause a segmentation fault, and that quickly terminates your program. So that's an overview of how information is stored in the machine.